All right, welcome to today's lecture. A couple of announcements. Homework 3, games, is out since last night, so you can get started on that. It's due next Monday. Project 2, which is multi-agent Pac-Man, where you get to play against the ghosts, is going to be released later today or tomorrow. Last time there was a bit of talk about additional opportunities to participate in the contest. So we've changed the deadline for the contest, just the contest. So Project 2 is due next week, Friday at 5 p.m. But the contest associated with Project 2, which is optional, is due on Sunday at midnight. So you have time after you submit your Project 2 to then participate in the contest. You don't have to do it before the deadline of Project 2. If anybody had an exam conflict and they emailed us by the deadline, which was this last week's Tuesday, you should have heard back from us. If you didn't, email us again, because that means somehow your email from before got lost. We have a survey out to consolidate your PandaGrader and edX user accounts. Please fill in that survey. Otherwise, we have no way to consolidate your two accounts, and you only have one of your grades, either just exam and written or just projects and online homework. All right, let's take a look at the results of the Project 1 mini contest. So some of you might recall, in Project 1 at the end there's an optional mini contest, and what you get to do is to control your two agents, which in your own camp are ghosts, but once you traverse are Pac-Man, to eat the food pellets, all but two of them, as quickly as possible and bring them back. If you do so more quickly than your opponent, then you win the game. Okay, we have 31 entries. We had some fun names there, some names that I cannot pronounce, but that look cute. We had a no effort, but despite the no effort, still beat 3 of the staff bots, so got 0.75 points of extra credit. Aiming for last, who ended up standing 15th out of 34, so not successful in some way. Let's look at the top 10. So in 10 we have Tupac, which is Casey Mofad. At 9 we have Test 111, which is Boyi Chen. At 8 we have I Like Big Bots and I Cannot Lie, Kenwa Song and YS Kim. At 7 we have Last Attempt, Roger Shen. At 6, OK Bot, pretty okay I guess, Aaron Zhou. At 5, Staff Too Good, Unhappy Face, Ton Hon Lai. And at 4 we have Bots Love, Joseph Hui and Alan Yao. Just a round of applause for our top 10 so far. Then for the medals, all right, the top 3 win medals, as you know. For the medals, we are left with, in alphabetical order, Artificially Retarded, Fanye and Tianhao Jiang, Too School for Cool, Austin Satterley, and Zephyr, Kevin Casey and Zayu/Andrew Liu. Okay, let's have a face-off between those and see who is better. So, essentially, to not stand third, we have a match here, and if you win, you don't stand third, but stand higher. Too School for Cool versus Zephyr. Note that the ranking isn't made based on just one game, but based on many games. But this is just a representative game, where on the right, in blue, we have Zephyr, which is eating the dots on the left. And from the left, the red team is Too School for Cool, which is going out to the right to eat the dots. And we see that the blue team in this case wins, and so we have Too School for Cool in third place in the contest. Not because of just this game, but through the overall average set of wins. Okay, so that leaves us with artificially retarded versus Zephyr for first place. Let's look at some of the things these teams put into their bot. So artificially retarded divides food into groups using k-means, selecting 2 groups that are farthest apart. Pick up other food that is nearby along path to target. Assign scores to food based on distances between both agents, food and finishing line. Keep in mind, finishing line here refers to you need to bring your food back to your own camp. It's not enough to just eat the dots. When the amount of food left is low enough, use search to find optimal path for remaining food. Zephyr has split the food into 2 groups, 1 for each agent, using a heavily modified minimum spanning tree. Start with greedy path through food for each agent. Randomly shuffle the path and compare to old path, keeping the new path if it has lower cost. All right, let's see how this plays out. Artificially retarded versus Zephyr. And again, keep in mind, it's not just this one game that decides the final ranking, but of course we picked the game that will make the one who won the whole thing also win this game. So, artificially retarded versus Zephyr. We have on the left artificially retarded, on the right Zephyr. And we see that Zephyr clears the board before artificially retarded, and Zephyr is the winner of the contest. Congratulations to both teams. All right, so this rounds out our entire top 10. We had 3, Austin Satterley, 2 School for Cool. At 2, Fan Ye and Tian Hao Jiang, artificially retarded. And at 1, Kevin Casey and Zheyu Liu with Zephyr. All right. Let's just do congratulations to everyone who participated. And a reminder that there is a Project 2 mini contest. And it gets, in some sense, more interesting, as now on your own side, your ghost will act as ghost. They will get to eat the Pac-Man of the other team that are on your side. If you eat a Pac-Man there, they lose all the dots, and the dots just sprawl out around where you ate Pac-Man, and Pac-Man gets reset to their own camp. Question there. Can we see the actual yellow ratings? Oh, the ratings? Let's see if we can see the full ratings here. Sorry, the second question I didn't hear. Can we see like the win rates against each bot on our own time? Yes, you can. If you go online tonight, this will be opened up for you to see what's going on. You'll be able to see what the ranking was. Maybe we can do this, maybe not, depending on Airbear's willingness. Let's do this after the break. During the break, I can try to get this to work, go online and pull up the full rankings with the ELO score so you can see the difference between the teams. All right, so topic of today's lecture, uncertainty and utilities. So we're going to deal with uncertain outcomes, which in practice happen a lot. Often you don't have a perfect model for the world, you don't know what's going to happen. Let's have a little reminder here of what we already looked at last lecture, which is this idea of Minimax games and kind of related to how sometimes maybe it's not the right model for what you want to do. So let's say this is your game. If we play Minimax, so the maximizer gets to play here, minimizer over here. These are the utilities for the maximizer. The minimizer's utilities are the negative of the utilities for the maximizer. So minimizer optimizing your own utility means minimizing the maximizer's utilities. And so if we play this out with Minimax, then the optimal utility here would be 10. We'd get 9 here, and at the top, Max would have 10 and would play off to the left. right, but now it doesn't have to be the case that your opponent has to be this perfect machine that always does the right thing. Maybe your opponent is not as good and might make mistakes at times. If that's true, you might not want to model that opponent as a minimizer, but you might want to model it as sometimes doing something else than minimizing. And maybe you might want to take your chances. Maybe you're willing to go off to the right because there's a small chance they'd make a mistake, and 9 is not that much worse than 10, and 100 is a lot better. So if your bot isn't perfect, we might want to use a different model, and we're going to introduce chance here in these trees. So instead of having a minimizer node, we're going to have a chance node, and chance nodes are denoted by circles. Note that chance can be caused by many different things. Chance could be caused by playing against an imperfect player that might make mistakes. You might also introduce a chance node here just because you don't know what's going to happen. You have nature making a decision for you. Nature is rolling dice, and that's why chance is being introduced. So it could be something you just can't model, or it could be actual chance that's happening. All right, so once this is the case, once we have a chance node there, and let's assume each outcome is equally likely, then, well, on the average here, you would get a 54.5. On the average here, you'd get a 10. And now you might want to play off to the right, because on the average, you'll do better. Okay, so what we'll do to solve these kinds of problems is something called Expectimax search. Very similar to Minimax search. We just do something different now. At the chance nodes, these are a new type of nodes. So most important thing right now to keep in mind is that the randomness could be either explicit through rolling dice, or it could just be unpredictability. It could be that you don't have a good model for the ghosts. You know they're not necessarily Minimax players against you. They might not actually roll dice internally. They might do something according to some system, but it's not exactly Minimax. It's worse than Minimax, and so you model them as randomness. Question there. In this first half of the lecture, I'm actually going to postpone questions till we are at the break, because we have a lot to cover since we also had the mini contest. And then at the break, we'll see if we can take some questions then and clarify right after the break. So opponents could be unpredictable. Another thing that could happen is that your actions are just unpredictable themselves. You could be a robot. You're riding along in maybe on slippery surface. Your wheels might slip, and you don't move where you ought to be moving if things were perfect for you. There's some noise there. The way to model this would be that after your action, a chance node kicks in that then decides where you actually end up. So your action doesn't directly decide where you end up. So different ways this could come about. What we're going to do is we're going to now optimize for the average outcome. So in this case, whenever you encounter an Expectimax node, an expecting node, which are the circles, rather than doing whatever we did before, you average the outcomes, and this could be a weighted average, right? If it's 50-50, you just have the average of the two. If one outcome is more likely than another one, you have weights associated with them, take the weighted average. Later, we'll see how to formalize some of this as a Markov decision process, but for now, let's just think of this as a modification to our Minimax game tree, where now we have chance nodes inserted. Let's look back at an example we looked at last time, where we had a game of Pac-Man, where remember we had this scenario here, where Pac-Man is essentially trapped by the ghosts. In a Minimax sense, this is a terrible situation. The best Pac-Man could do was to suicide as quickly as possible to end his losses as soon as possible. If we play Minimax, which we're going to see now, that's exactly what happens. Now, we saw that, on the other hand, if the ghosts were playing randomly, then that would mean the blue ghost could go up or down, either direction. And if the ghosts were to start going down, then Pac-Man could follow the ghost, eat all the dots, and win the game. And so then Pac-Man shouldn't necessarily suicide. We don't know whether the ghost would move up or down. It's actually random. We don't know in this simulation what's going to happen. But we know that on the average, half the time the ghost will move up, half the time the ghost will move down. And so the Expectimax right thing to do here is to actually follow the ghost and go off to the left, follow the ghost till the ghost moves away, hope that that's what happens. If it doesn't happen, then it was just bad luck. So let's see what happens here. It's the lucky scenario. The ghost moved away, and so we see in this case, you get a very high score. That doesn't mean this happens every time. Half the times this will happen, half the times you'll still get eaten very quickly. You'll do slightly worse than if you had played Minimax in those bad scenarios. You'll do a lot better in the good scenarios. Okay, so what does this look like in code to run Expectimax? We'll still have a dispatch function. The dispatch function checks if it's a terminal state, return the state's utility. If it's a maximizing player's turn, return the max value call for that state, for which we'll have a separate function. If it's an expectation node, which means we're going to have a random outcome, then we call expected value. Here are these two functions. The max value we've seen before. Expected value looks a lot like max value. But while we're still cycling over all successors, now we're averaging them here, taking a weighted average over the values of the successors. Again, the value of the successor will be a recursive call to this dispatch function. That successor could again be an expected node, it could be a max node, whatever it is, dispatch node will take care of that. All right, so fairly straightforward. Now, let's say we were to run this on this example here, what will we get? We have a weighted sum here of utilities, so we end up with 1/2 times 8 plus 1/3 times 24 plus 1/6 times minus 12, which will give us 4 plus 8 plus minus 2, which is 10. And so we'd have 10 over here as the value of that node. All right. So if we run this on a full game tree, let's see what happens. Let's assume all outcomes are equally likely. So each outcome is a chance of 1/3 once you reach the node above of it. Then we'd have a value here of 8. We'd have a value on the next one of 4. We'd have a value here of 7. Then when we go a level up, that's a maximizer node. We end up with 8. And we play this direction. After we play in that direction, chance will determine what the outcome is. In Minimax, if everything played out as we assumed, we'd actually get the value at the top node. In Expectimax, that's not true. There's actually no node at the bottom have a value of 8. You'll never have an outcome of 8. On the average, your utility will be 8. But in any given outcome, in any given play, you don't know what the outcome is going to be. Sometimes it'll be 3, sometimes 12, sometimes 9. It'll average to 8. At the end of last lecture, we looked at something called alpha-beta pruning. And the idea there was that once you inspected some nodes and you're going further down the tree, you could sometimes decide that some part of the tree you can just skip, because there's nothing there that would affect what would the outcome of the game be. Let's see if that still can happen here. So in Minimax, if we were to work through this tree, once we reach this point over here, with a value of 2, we'd have, this one was 8. So far we have, as our best value at the top, 8. If this were Minimax, we saw a 2 for the opponent, our opponent, minimizer. We'd say, well, no matter what is here, it's only going to make the value lower than 2. There's already an option of 8. So Maximize would never let this happen, to let the game get down there. So we don't even need to look at what's on those question mark values, because no matter what, that's not going to happen. With Expectimax, that's not true. Because what if, for example, the value here were plus infinity? Then that all of a sudden would make this a really good option. And so what you see here is that unless you have some bounds on what the values at the bottom nodes, what the utilities could be, unless you have some bounds, there's no way to do pruning unless because it always could be that there's this really high or really low value that turns things around. So unless we have bounds on the values that we might have at the leaves, we can't do any pruning for Expectimax. We also saw last time that if you run search in a game tree, and in this case we have a game tree where first Pac-Man plays, then the ghost is assumed to be random, the next ghost is playing, it's also assumed to be random, then it's Pac-Man again. We saw that it's impractical to search all the way down to the bottom of the tree. It's typically too deep. So we would cut it off and use an evaluation function. We'll do the same thing here. Just like we did for Minimax games, for Expectimax games, there's some depth we're able to achieve. At that depth, we use an evaluation function and then propagate those values up. So over here, we'd be averaging the 400 and the 300, maybe in a weighted way if there are weights on those branches. All right, so these are just estimates, which means that the top will just get the estimates, but that's the best we can do with a finite amount of computational power. All right, so what we have now is on these splits that are ruled by expected nodes, we have probabilities. And as you'll see, as the semester goes along, we'll start looking at more and more probability computations. For today, it'll still be fairly straightforward, but we'll do a quick review of the things that we do use today. So to formalize probability theory, there's this central thing called a random variable. The random variable represents an event for which the outcome is unknown. And you can't choose what the outcome is going to be. It's going to be set for you in some sense by nature or by some process that you don't have control over. And all you have is a probability distribution. And a probability distribution gives you weights indicating how likely each of the possible outcomes are. For example, we could have a random variable for modeling the fact whether there is traffic or not. We could have a domain for this random variable, just like we had domains for variables in CSPs. And maybe the values could be no traffic, light traffic, heavy traffic. The distribution could be 25% chance no traffic, 50% chance light traffic, and 25% chance heavy traffic. One thing that's always going to be true for these distributions, as hopefully you already know, otherwise you might run into a lot of trouble throughout the semester, that for probability distribution, these weights have to sum to 1, always. All the weights are positive and they sum to 1. This distribution could be something else. You might not agree with this. You might want to model this completely differently. You might say traffic is not a discrete variable. It has to be a continuous variable. I'm going to measure traffic by the density of cars per square foot on the highway. Now you have a continuous valid random variable. You have a density function. That's fine. That's a fine model too. Here we'll be working with this model. Just like we've seen in search and other problems, some models are more accurate but might be more difficult to work with. Other ones might be not as accurate but good enough and easy enough to work with that we can do something with them. We'll be working with these discrete models here. We'll see more laws of probability later, but for now, keep in mind probabilities are always positive, 0 or higher than 0, between 0 and 1, and they have to sum to 1. One really important thing we'll look at a lot in the second 1/3 of this class is how to update probabilities as we get new evidence. So we'll do things like, okay, maybe initially the probability for heavy traffic is 25%, but now that somebody tells us it's 8 a.m., which is a time at which traffic tends to be heavier, we update our probability to be 60% for heavy traffic. And a lot of what the second 1/3 of this course will be about is how to do these updates when you have lots and lots of random variables. All right, so the other thing we're doing today with probabilities is computing expectations. What is an expectation? It is, you have a random variable that has a numerical value, and then you take the weighted sum of the outcomes for that random variable. So, for example, how long to get to the airport, if the probability distribution is over traffic is the following, and maybe the time associated with that is 20 minutes, 30 minutes, 60 minutes, then the expected time to get to the airport would be a weighted sum of these, so you'd have 0.25 times 20 plus 0.5 times 30 plus 0.25 times 60. Whatever that gives you here, I guess in this case it would be, is it 35? $35 minutes would be your expected value for that random variable. This is like our expected utilities if you play Expectimax. It's not an outcome you're likely to see per se. It's just over many runs, on the average, this is what you would get. All right, so 35. What probabilities do we use for now? For now, we'll assume that they're provided to us by, let's say, the probability fairy who comes in, says these are the probabilities on each of the nodes. Where do they come from? Where does she get them from for us? Well, if you had a roll of a die, it could just be a uniform distribution. The model could be very sophisticated. It could require a great deal of computation. It might be that, and you'll see that much later in this course, you might have to do computation in a Bayesian network, which models a distribution over many random variables, and only the result of that computation can tell you what those probabilities are. It could be that you have to compute something about your opponent. You have a model of your opponent, and you have to do some computation based on that model, and then that gives you a distribution over what the outcomes are going to be. It could come from many places. Somehow we assume that we get a distribution there, and then we can do the weighted averaging to compute the Expectimax value. All right, so let's do a little test here to see if we kind of all got this. So let's say you know what your opponent is actually, let's say you know your opponent is running a depth 2 minimax. Using the result of that depth 2 minimax 80% of the time, and moving randomly the other 20% of the time. What tree search should you use to compute your optimal move? Let's take 30 seconds for you guys to think about this, talk to your neighbor, and then discuss what you think should happen here. All right, let's see what we got here. Who thinks we should run a standard minimax search? Nobody. Awesome. Who thinks we should run an Expectimax search? All right, great. Let's go all the way to the back there, in white shirt. Expectimax search. How is this going to work?
You would run, or you would weight what their result from the minimax search would be with a 0.8, and then you average all possible values, and then give that a 0.2 weight, and then after step 2, you would just average all possible values and give it a 0.3 the full weight.
Great. So that was a perfect answer. I'm just going to repeat it just to make sure everybody can hear it because the student didn't have a microphone. So the answer was we're going to do something that looks like this. Expectimax search. This is your opponent. There is randomness in how they move. And in fact, there's a lot of computation that needs to go into how they move. You actually have to do a search inside your search. So as you want to compute what the distribution is there, you run a depth 2 minimax. The result of that depth 2 minimax is some action. You say, well, now I know what the depth 2 minimax action would be for my opponent in that particular situation. Then that action already gets an 80% chance. Then between the two actions, you still have 20% chance to distribute. 10% goes on top of the 80%, and the other 10% goes to the other action. So what you see happening here is that you're kind of running a search inside a search. Remember the very first slide when we started talking about games and had this slide where the agent was thinking about what the other agent is going to be, who is thinking what the first agent is going to be, who in turn is thinking what the second agent is going to do, and so forth. We talked about that, and then we never actually saw this into play. We always saw just this one minimax tree where there was none of this recursion happening where we have to think about the other one and so forth. But here it is happening. And in general, this will be happening. The only times this doesn't happen, that you have to do this thinking about the other player and so forth and do this side searches inside your search, the only times this doesn't happen is when both players' models coincide and they have the same model. So if you are a maximizer, the other player is a minimizer, and you both model each other as maximizer and minimizer, then everything just comes out as one tree. But once there is any mismatch there, where you are, maybe one player is a minimizer, but you model it as an Expectimax node or the other way around and so forth, then you start having this recursion where you need to have searches inside searches and so forth. All right, so this brings us to modeling assumptions. We've seen in regular search that modeling is really important. How do you model your world? And that'll affect what kind of outcomes you get. We've now seen two ways in some sense to model opponents, as minimizers or as random players, and there are downsides to both. There are dangers of both optimism and pessimism. What's the danger of optimism? Well, it's assuming that whenever the world does something, it's just chance, but sometimes the world will work against you. Let's say you are an agent and you're about to enter a cave. The cave is full of monsters. An optimistic agent would say, well, you know, there's a reasonable chance the monsters won't bother me and just let me walk through. But that chance might be pretty low, and that might not be the right way to think about it. On the other hand, a very pessimistic agent sees everything as in its worst possible case. He might run into a beautiful bunny. He might think it's some vampire bunny that will suck the blood out of the robot. So, especially the second case here, you could imagine that if you're always pessimistic, you model everything as a minimizer, right? You can pretty much do nothing. You can't leave your house because it could be that some driver on the street, rather than trying to obey traffic rules and you can expect how to avoid them, they're just out there to drive into you and that's it, right? So pessimism is really dangerous. You don't want to model things too pessimistically or you get very non-meaningful outcomes really of what your prescribed optimal actions are under the assumptions of pessimism. Let's take a look at this in the context of Pac-Man. So what we're going to look at here is two choices we get to make. First of all, the ghost could be adversarial or the ghost could be a random ghost. That's how the world is. Two possibilities. Then there are two possibilities on how we model the ghost. Pac-Man could play as a Minimax agent, or could play as an Expectimax agent. And so we have a total of 4 possible scenarios here, depending on each of the choices. Let's take a look at how this plays out. So first, let's take a look at matched assumptions that we've seen the most of in last lectures. So the first assumption here is we have a adversarial ghost, and Pac-Man plays Minimax. So Pac-Man, it's in this case a depth 4 Minimax, Pac-Man stays away from the ghost, and then when the ghost makes its move, circles around and can go eat the food pellet. All right. Now let's take a look at, again, matched assumptions. Pac-Man plays Expectimax, and the ghost is also random. So this is how this plays out. Pac-Man moves toward the dot because it doesn't think the ghost is going to eat it, and it works out well. Well, the ghost is random, so it's not going to play out the same way every time. Let's see how it plays out this time. Still plays out pretty well. It gets the dot much sooner than in the Minimax case. Again here, so usually this Expectimax thing seems to work out pretty well. If we play this long enough, sometimes it won't play out all that well. This is why we need extra time this lecture, it seems. So here's where the optimism was a little too much in that particular playout, but on the average, this optimism of indeed thinking of the ghost as a random player worked out pretty well. Now let's look at a mismatch scenario. So in this case, the ghost is a smart ghost, but Pac-Man is modeling the ghost as a random ghost. So a little too optimistic. Let's see what happens. Ghost is not that smart. The ghost can only search so deep. It doesn't search deep enough to be super smart. But we do see that the ghost is reasonably smart, and think of it as just a random player is not playing in Pac-Man's favor as often as when it's actually a random ghost. All right, here's another mismatch scenario. We have, in this case, Pac-Man is playing Minimax. The ghost is random. So think about what you expect to happen here. Pac-Man's going to be very cautious. Even though the ghost is just wandering around and not really trying to chase Pac-Man, Pac-Man will try to stay as far away as possible from the ghost until it's really sure that it can make its way around the ghost and get to that food pellet. And the ghost is just moving randomly. Still not safe. This random ghost is slowly making it up. Almost. There we go. So that's Minimax play. So let's look at some averages here. If we have the match scenario, a adversarial ghost with a Minimax Pac-Man, Pac-Man can win here because one ghost can't really trap Pac-Man. So we win 5 out of 5, but the score isn't super high because sometimes it takes a while before we win. This gives a score, average score 483. If we have the other match scenario where we have Expectimax Pac-Man and a random ghost, that's of course an easier scenario because the ghost isn't working against Pac-Man. We play Expectimax, takes advantage of that, and on the average we have 503. If the ghost is adversarial and we play Expectimax, well, we don't win all that often. If we play it out enough, in this case, this ended up winning 1 out of 5 only. We get an average score of 303, minus 303, so very bad. And then here, the other mismatch scenario, we have a random ghost, we play Minimax, we win 5 out of 5, average score of 493. Compare those two, right? In one case, Pac-Man is tailoring its strategy, knowing the ghost is random, and playing optimally on the average for that scenario. Whereas in the other case, Pac-Man's playing it safe, still wins 5 out of 5, but the average score is lower. All right, there are other game types. There's not just random two-player games, where one of them might be Minimizer, Maximizer, Expectimax. You can have mixed layer games, where you have Maximizer nodes, Minimizer nodes, and random nodes. Backgammon is an example of this. In backgammon, essentially before you get to make a move, you roll dice. The roll of the dice is a random node, a chance node. After that chance node has played out, you get a set of choices. Could be, let's say the Minimizer gets a set of choices, makes it move, then it's another chance node, roll of the dice, then the Maximizer gets to make a choice, and so forth. It doesn't really matter how these are ordered. You can always use the same code to solve these kind of games. You just have a dispatch node that checks what kind of player gets to play right now, and then minimize, maximize, or weighted average over the children accordingly. So backgammon is actually one of the first games, maybe the first game in which AI was able to play really well. So in backgammon, the way it plays out, there's 20 legal moves for a given roll of the dice, but there's a lot of possible outcomes of your rolls of the dice. So it has a very large branching, it has a large tree because you branch on chance nodes and on moves. Then as the depth increases, the probability of reaching a given search node shrinks. So each particular path down the tree has a very low probability. And there's a lot of them. So there's a lot to consider to get a very accurate computation of the outcome. Pruning is tricky because there are chance nodes. At the same time, the fact that there are chance nodes makes it a little easier to get evaluations of certain states of the game, because there's a lot of randomness, there's a lot of averaging out of possible scenarios, which often makes it easier to come up with an evaluation function than when you're playing a Minimax scenario where just one wrong move might completely change the value of the game, right? Here, it's not often that one slight change in how you play will all of a sudden drastically change the value of the game unless you're all the way at the end. Historically, we had this AI called, well, Gary Tesaro built this AI player, TD Gammon, uses a depth to search. It's not super deep, but pretty deep for the 50s. Very good evaluation function. We'll see when we look at reinforcement learning how we can learn a good evaluation function through self-play, and generated world champion level play. It's actually the first AI world champion in any game. There are other types of games. It's possible that you don't just have one value at the bottom, but that there's many players, and each player has their own utility. In this case, there are 3 players. Each player has their own utility. There's a red player, a blue player, and a green player. For every outcome of the game, there are 3 values. 1 here is the utility for the red player for this outcome of the game. 6 is the utility of the blue player, and 6 is the utility of the green player. This is the most general case, right? The Minimax games we've looked at can be modeled this way. If you had a Minimax game, think about it, let's say you had a Minimax game, a maximizer followed by a minimizer, and then a utility here, let's say 5 is how we drew it. And maybe we have 2 and 10 here. Really what's going on is that we have 5 for the maximizer, and we have -5 for the minimizer. And we have 2 and -2, and we have 10 and -10. That's what it looks like in this format over here, where each player explicitly gets their utility annotated in the leaf nodes. The reason we haven't been doing this is because for a 2-player game, if the minimizer's utility is the exact negative of the maximizer's utility, then there is no point in putting 2 numbers there, because 1 number is enough to encode all information. But in general, this is what it looks like, and the Minimax games are just a special case of these multiplayer games. All right, so what kind of things can play out in these multiplayer games? Let's look at this subtree over here. If red were to move left, what's going to happen, right? Well, let's take a look at what happens at the bottom here. The green player, it's still that we have to start from the bottom. The green player will just look at this 6 and this 2, and we'll say 6 is better for me. That's all they consider. They don't care about the other utilities. They don't care about minimizing other players' utilities. If they cared about other players' utilities, their own utility function would already have that encoded in there. And so their own utility is all they have to look at. 6 is better than 2, so green would go this way, and the outcome would be 1, 6, 6. So that's the value we propagate up is 1, 6, 6. Over here, 2 is better than 1, so we get the 6, 1, 2 outcome, if the game were to get there. Then it's blue's turn. Blue is the second number. 6 is better than 1, so blue would go this way, and we'll get 1, 6, 6. We can do the same thing in the other subtree on the right, and then we can propagate up for red based on the first number. Now, what's interesting here is that in this subtree over here, what we see is blue and green are actually aligned. For both blue and green, this is the best outcome, and they both steer towards that outcome. If red goes off to the left, plays off to the left, blue and green will channel it right over here, where they both get 6, which is the best thing in that subtree. So you get collaboration here. Both of them collaborate to get the best possible outcome for each one of them. But it just naturally emerges due to their utilities. We don't hard code anything about blue and green have to collaborate. It's just these utility values make them collaborate once you hit this point. It doesn't always have to be the case. For example, over here, green would go for the 5 over 1, so it'd go this way, which is great for green, but not good for blue and red. So there, green is not collaborating with blue. If we were to reach this point, green is not playing in favor of blue. Well, so that's just what you can get. You can get very difficult, kind of complicated scenarios to play out just based on putting utilities there that are not just the exact opposites of each other, where some subtree players collaborate, work against each other, and so forth. to compute the outcome of the game if everyone plays optimally, still just a matter of propagating up. So let's just do it here. Green prefers 7 over 2, so we get 5, 1, 7. Prefers 5 over 1, so we get 5, 2, 5. Then blue prefers 4 over 2, so we get 5, 4, 7. And red prefers 5 over... Say it again? Oh, that's a 1. That's not clearly written. Blue will not prefer 1 over 2. Thank you. Blue prefer 5 to 5 outcome. Then red gets to choose between 5 and 1. 5 is better, so red would go this way. And the final utility, if everybody plays optimally here, would be 5 for red, 2 for blue, 5 for green, and we'd go down this path over here. All right, so this could go with 3 players, any number of players. You can just have dispatch nodes. The dispatch node checks which player is being played for, then checks what is the best option for that player, propagates that set of values up. All right, let's take a break here. So one question I want to touch on that came up during the break is, well, in this scenario here, the green player might not know the utility of the blue player and the utility of the red player. So how would they do this computation? I guess, how would you propagate things up, right? And how would you know, if you're the red player, how would you know how the green player is going to make choices? You can't do this computation if you don't know everybody's utilities for every outcome. So in this scenario here, we assume that every player has access to every other player's utility function that tells them what the utility would be for each player for each possible outcome. Otherwise, there's just no way red could do this computation and decide that going right is the right thing. Will you in practice always know what the other player's utilities are? Not necessarily, right? Think of this, for example, for playing Pac-Man. Let's say you're playing Pac-Man against another student's agent in, let's say, the Project 2 mini contest. You might have a hunch. You might say, well, I think they play depth 6 Minimax with alpha beta pruning because I know that's how deep I can search and I really optimize my code. They're probably not searching deeper than that. But then to know what they're going to do, if you really want to predict what they're going to do, you'd also have to know their evaluation function. So what you'd have to do is you'd have to play multiple games against them, see how they act, see what evaluation function that you might hypothesize is consistent with how they acted, and now maybe you build a model for how they make decisions and you can do better. You can anticipate mistakes they might make and so forth, especially if you can search even deeper than they can. All right, let's say you play against a player that only looks 2 deep, and you can look 6 deep, and you know what their evaluation function is. You can definitely take advantage of that to then do better as you play against them. In the next to last lecture, we'll look at another setting where something similar will happen. There's a lot of robotics problems actually that I myself have looked at for my PhD thesis work, where you want to give a utility to a robot, right? And then the robot's supposed to optimize that utility, but you don't know what the right utility is to give to that robot. And then if you give the wrong utility to the robot, then that robot will optimize this wrong utility and all of a sudden it's doing the wrong thing, right? If you have a vacuum cleaner robot and you give it a utility to drop off dirt everywhere, obviously that's completely the wrong thing. It will optimize that wrong utility, things will go wrong. People don't make that kind of mistake, but it turns out once you have a lot of things to care about, just like we had in evaluation functions, let's say you have 25 features you care about, it can get tricky to decide how to weight each one of those 25 features. And then we'll see towards the end that there are algorithms that can recover how somebody is weighting those different features. And once you do that, then you can give those weights to the robot who can now optimize whatever that person was optimizing and do things right. That gets us to the whole point of where do these utilities come from, right? Maybe for this little robot here, ice cream is a very high utility. Don't know where that came from, but We have a lot of questions to answer here. We've seen something very mechanically here so far. We've said there are utilities. We're going to average them when there is randomness among outcomes. We don't even know why averaging is the right thing to do, right? Minimax could be the right thing to do. Depends on what we care about. Do you care about your worst case scenario being not too bad, or do you care about on the average doing well, right? When could we justify averaging utilities? In the very first lecture, we actually said, AI is about maximizing expected utility. So that's maximizing what we've been talking about in Expectimax here, but we haven't really shown why that's true. Okay, so in the next part of the lecture, what we're going to look at is essentially why we're doing what we're doing. Where do these utilities come from? How do we know utilities even exist? How do we know there will be such numbers that we can use and then with those numbers do the right thing? How do we know that averaging them is the right thing to do? And related to how do we know they even exist? Is it possible that maybe the preferences we want our robots to have cannot be described by utilities? Need a different formalism to describe the preferences. All right, let's first look at this simple example over here. If we play this out as a Minimax game, the one on the left here, what will happen is we'll brace for the worst, and we'll say, well, that means as a maximizer we have to go right because then we can at least guarantee 20. And the game will play out this way. If we now change our utilities, square all of them, it'll play out exactly the same way because squaring utilities will not change their ordering. And the only thing that affects how we play in a Minimax scenario is the ordering of the utilities. So we'll still play this way. All right, so Minimax is insensitive to any monotonic transformation to utilities. Just cares about the ordering. But what when we start averaging? Let's see what happens. Let's say we start averaging. Let's take a different color. So we'll go purple for Expectimax. Expectimax has a value of 30 here, a value of 25 here. So Expectimax will play this way. We square the utilities. We have an average of 800 over here, an average of 650 over here. Is that true? This is 20. So we go this way in the first scenario, we go the other direction in the second scenario. So for Expectimax, squaring the utilities changed the way the game was played. So all of a sudden, when we're in the Expectimax scenario, it's not just about having a utility function that orders things the right way, it's also about getting the magnitudes right. Because the magnitudes will affect how we gauge the quality of a particular outcome. All right, so where do these utilities come from? We now need to start putting numbers on them that are precise. So let's start thinking about that. So utilities are functions from outcomes of a game, let's say, or outcomes in the real world to real numbers. So you go from outcome to a real number for each possible outcome. Ideally, they relate to the utility, the preference the agent has. In a game, it could be simple to assign them. +1, -1 for a win versus loss. What's important is that whatever you assign as utilities define the agent's goals. So it's your job to assign utilities that then will have the agent behave in a good way. So far we've hardwired them. We've always done that for our agents. You could say, well, a really smart agent. Wouldn't a really smart agent just pick their own utilities? Well, not really clear what that would do. You say this agent picks their own utilities. Well, I mean, you're not defining what the goal is for the agent. You don't give them a goal. They might pick a goal that's just not useful to you. And once you constrain the agent to pick a goal that's useful to you, well, then effectively you are defining utilities again, right? So you can't just let an agent pick their own utilities. They'll optimize in a very easy way. They'll pick something and then not align with whatever you want it. You could say, well, if we have to hard code these utilities to describe what we care about, why don't we just hard code the behavior? Isn't that more direct? If I know I want a vacuum cleaner robot to pick up dirt, why don't I just program it, move to the nearest dirt, once you're above it, suck up, and then repeat? That'd be a reasonable way to program your vacuum cleaner robot. But it's more complicated, it's difficult. What if there's an obstacle between the dirt and the robot? What should it do? Now you need to say something like, oh, maybe move to the right around the obstacle if there's space, and so forth. So building a reflex agent is really difficult to do well. That's why we like to just specify utilities and let the Minimax or Expectimax algorithm take care of the rest. All right, so let's look at an example here, ice cream example. Let's say you could go get ice cream. You can get a single scoop or a double scoop. Single scoop might make this toddler robot really, really happy. Double scoop could lead to a disaster where it loses all its ice cream. Very bad outcome. Or it could be the best of all worlds and have the 2 scoops to enjoy. What we know how to do is how to rank these. We know this outcome over here is the most preferred one. This is the second most preferred, and this is the least preferred outcome. But to run Expectimax and to know what the right thing is to do, ask for a single scoop or a double scoop, we actually need to associate numbers with these outcomes. And we need probabilities here. We need numbers associated with these outcomes so we can average these numbers and compare what's the expected utility of the double scoop versus the expected utility of the single scoop. All right, so we're going to define these numbers going through preferences. But what will be important to be able to define those numbers is to allow for lotteries. So what I mean with a lottery is not that you go buy a lottery ticket. It means something technical here. What it means is that you're in a scenario where there's more than one possible outcome and there's a distribution over those outcomes. So as an example lottery, capital L here, is one where there are 2 possible outcomes, A and B. And A is a probability of P, B is a probability of 1 minus P. We will look at preferences. So the way we denote preferences is as follows. That means A is preferred over B. This here means A and B are equally good as outcomes. All right. What we're going to do now is to consider both utilities for, or preferences over prizes that are guaranteed. A is a prize, something you're guaranteed to get if you're in that scenario. Or you could have a lottery where there's a distribution over outcomes. Each of them has a prize associated with them. All right, so keep in mind, it's not about scratching lottery tickets. It's not about the pleasure of not knowing what's going to happen and the thrill of, I don't know what the outcome is going to be. That is not encoded when you put a lottery down this way. You could encode that. You could say, well, the outcome is not just this prize, but it's also that I have had the thrill of being part of a lottery. You need to put that explicitly in A then, and in B, that you enjoyed the thrill. All right, so now we're going to look at a set of actions, and that set of actions will lead us to utilities that are formally justified. So the way this works, right, this is standard math. You come up with a set of actions that you're willing to agree upon. You say, these are actions I'm happy with. And then you start looking at things that follow from those actions. If you're not happy with what follows from those actions, that means somehow one of these actions you really shouldn't be happy with because it's just a consequence. And the game is also one where you have a minimum set of actions. Typically, you don't want to assume too much. You want to assume as little as possible so that you can get somewhere. So first thing we're willing to assume, and what we're going to do here is that preferences are transitive. If you have 3 prizes, A, B, and C, if you prefer A over B, and you prefer B over C, then you must prefer A over C. You could disagree with this, but this is an action we're going to work with, and there's a lot of justification for this to be a reasonable action. Let's say there was this little naive robot over here, and that little naive robot prefers B over C. That means if that little robot is holding prize C and you have B, you could give that robot B, get C in exchange, and that robot would even be willing to give you some money on top of that, let's say a penny, because it prefers B over C. So you made a trade and got a penny. If in addition, that little robot prefers A over B, well, then if you had A available, you could trade A for B that they just got from you. And as you get B back from them, you also get an extra penny because they preferred A over B, maybe preferred it by a penny, let's say. Then if they also prefer C over A, you can now go again a third time to this little robot and say, well, you prefer C over A. I have A. You actually just gave it to me. You prefer C over A. I can give you A if you give me C and a penny. Sorry, I can give you C if you give me A and a penny. What just happened here is that you went through a cycle. Every step along the cycle, you got a penny from that robot, and you ended up with the robot still having what it had initially, which is C, and you still having what you had initially, which in this case is B and A. So sometimes nothing changed in terms of price distribution, but then you went through the cycle, you got 3 pennies. So this is an example of why it's reasonable to make this assumption that we have transitivity of preferences. All right, but keep in mind, this is not a proof, right? An axiom is not something you prove. We don't prove this, we assume this. And we just give justification as to why we're happy with assuming this. Okay, we have a couple of other axioms. Orderability. This is saying that you must either prefer A to B, or B to A, or you must be indifferent. One of these 3 must be true. Transitivity we already looked at. Continuity, this is a little more subtle what's going on here. It's saying that if A is preferred, if you prefer A over B over C, then there must be a probability P, a number between 0 and 1, such that the lottery between A and C, where A is probability P and C is probability 1 minus P, is equivalent to B. Because P is between A and C, you're willing to exchange B for a lottery between A and C as long as the weighting is correct. Substitutability is saying that if A and B are the same to you, you're indifferent between them, then a lottery that involves A is the same as that exact same lottery, is equally preferable as that exact same lottery where you substituted B for A. Right? Substituted B for A. Monotonicity is that if you prefer A over B and you have a lottery with probability P for A and 1 minus P for B, and you compare that with another lottery where your probability for A has gone down compared to probability, and probability for B has accordingly gone up, then that new lottery is less preferable. Okay, a lot of people will say these axioms are reasonable. There's a reasonable way to define what preferences should satisfy. If your robot follows those axioms, then we'll say that robot is a rational robot. So it gets a stamp of approval, rationality confirmed for this robot. Now here's a very interesting theorem. There's a theorem, and a theorem is something you can prove. We're not going to look at the proof, but you can prove that if these axioms hold true, then that implies that optimal, or that is rational behavior, can be described as maximization of expected utility. So accepting these axioms means accepting that there is a utility function, and if you use Expectimax with respect to that utility function, you'll be optimizing according to your preferences. All right, so this theorem is by Ramsey and then refined version by von Neumann and Morgenstern. Specifically what it says is that there exists a utility function. If you are happy with those axioms, there exists a utility function such that for any 2 outcomes, A and B, if you prefer A over B, then the utility of A will be higher than the utility of B. Also, your utility for lotteries will satisfy this property over here, that the utility over distribution over a set of outcomes is equal to the weighted average of the utilities of these outcomes. This is what we've been doing in the chance nodes of Expectimax, and this theorem is saying that that's the right thing to do. All right, so the maximum expected utility principle is then saying, well, all you need to do is maximize expected utility. That will follow, that will be acting according to your preferences. Does that mean you need to run Expectimax to be a rational agent? Think back to the first lecture. No. You could sometimes hard code a set of actions that happen to coincide with the irrational behavior, right? Okay, how about human utilities? Because that now becomes critical, right? Unless we want robots to just rule us according to their utilities, we need to specify utilities according to what we care about, put them in there and make the robots or whatever computer system is doing something for us optimize our utilities. So what are they? How do we get them? One way to get at them is to normalize utilities. So you put them on a scale between 0 and 1. The idea is that you have one outcome that's the best possible outcome ever, another outcome that's the worst possible thing that could happen, and everything else will fall in between. And the worst possible thing gets a 0, best possible thing gets a 1, everything else gets in between. You still might need some kind of scale to put this on, so one thing people might use is micromorts. That is a 1/1,000,000th of a chance of death. It can be useful for paying to reduce product risk and so forth, right? If you put something out there and you want to put some value on reducing risk of death. Similar measure is quality adjusted life years. Somebody is very sick. Sometimes it's not just about how long they will live, but the quality of the life matters, and you might then adjust your measure for the level of life quality in each given year they have left. All right. One thing that's important to keep in mind here is that the behavior that we look at is all invariant under these transformations. So we can't nail it down more than this, right? If you have a utility function u of x, and somebody changes it into a new utility function u prime of x, that is just k1, which is a positive real number, times u of x plus k2, optimizing expected utility will result in the same behavior for u and u prime. So we know we can't nail it down in an absolute sense. We can always shift utilities and rescale them. But that's kind of what we have available to us in terms of variability. This also means that we can put it on this. If we really have a best possible event and a worst possible event, we can shift and rescale to make everything fit in the 0-1 interval. All right. If you're only looking at deterministic prices, we can't do this. What we really need to do is we need to start looking at lotteries and ask people what they prefer between lotteries to make this work. So how are we going to do this? The standard approach is something like this. You get to spin some wheel that has some probability distribution and you get to choose between things. Sometimes on the wheel you might get an outcome that's death, instantaneous death. If that happens, boom, you're dead. There are other outcomes. And now you can start thinking, well, would I prefer to spin this wheel of potential death, or would I prefer to pay maybe $30 to not have to spin this wheel? Or maybe I prefer to pay $50 to not spin the wheel, and so forth. So that's the question we're asking here. And that's what allows us to put numbers on all possible outcomes, really, that are all unified as utilities. So best possible price, U plus, probability P, worst catastrophe, some U minus, probability 1 minus P. If that's what a price A corresponds to, then the utility of A is P times U plus 1 minus P times U minus. And so here's the example we talked about. What do you want to do, right? You want to pay $30 or play this game. If, let's say, instant death was your worst possible outcome, the utility was, let's say, 0, and no change was your best possible outcome. It doesn't have to be, but let's say it is. Then this would have maybe utility of 1, but in general this could be U plus and U minus. And now you could say, well, if this has a probability of, let's say, I don't know what it would be for you guys, maybe, let's just keep it abstract maybe, so 1 minus P and P. If you're happy, equally happy between playing this game and paying $30, then your utility of $30 is equal to 1 minus P times, well, it's negative $30 really because you're paying it, so your utility of losing $30 is 1 minus P times U plus P times U minus. And now you can do this for everything, right? You can either ask people for probabilities, you can say, well, what do you think about losing your bicycle. Would you prefer to lose your bicycle if the game was played with a probability 0.1, 0.2? Once you nail down the number, you can compute the utility of that person getting to retain their bicycle and so forth. So this gives us a way to put everything on one scale. All right. So for maybe some people, this would be a micromort would be equivalent to paying $30. Not sure. Depends on how much money you have, I guess. So how does money come into all of this? So we know there's this one currency, money, that you can exchange for pretty much everything in life, right? You buy whatever you want to buy if you have enough money. Money does not have to behave as a utility function. It is not the same as utility. That's one really important thing. When you're given a lottery, let's say, this type, probability P, outcome, you get X dollars, 1 minus P, you get Y dollars, then the expected monetary value is the average amount of dollars that you're going to get. But the utility of the lottery is something different. The utility of the lottery is the average of the utilities. And this is not the same thing. So, two different things, expected monetary value versus utility of the lottery. And often, the utility of the lottery will be smaller than the utility of the expected monetary value of the lottery. What is this saying? It's saying that people will often prefer to be guaranteed this weighted average in terms of dollars over having to deal with a lottery between those possible outcomes. That's what this equation is saying here. It doesn't have to be true. Everybody has their own utility. You can have a different utility, but often this is what's going to be true for most people you'll encounter. That means people are risk averse, meaning you try to avoid risk. You rather have a guaranteed certain amount of money rather than a lottery between a lower and a higher amount. When people are deep in debt, it might be the other way around. They might say, well, you know what? I'm already so far in debt, I'm never going to be able to repay this. So might as well take another gamble, and if the gamble comes out well, that's great, I'm out of debt. If it comes out wrong, well, I'm still just so deep in debt, I'm not going to be able to repay it. So that's what the curve looks like. And if you look at utility as a function of amount of money, you get some kind of saturation here in the positive direction, right? Very simple way to think of this is, who wants $1 billion? Who thinks $1 billion would change their life in a way that could benefit them, right? You do a lot of things. You can think of all kind of things you would do with that. Once you have your first $1 billion, you get a second $1 billion. It's not as much you can do on top of what you were already doing to enjoy your life. So there's some kind of diminishing returns there. That first $1 billion is so much more life-changing than that second $1 billion. If that's true for you, your curve looks like this. You get diminishing returns. Utility doesn't linearly increase. If your second $1 billion is as valuable as your first $1 billion, your curve would look like this. If your second $1 billion is even more worth to you than your first, which is going to be a rare person, but who knows, then it will look like that. All right. On the opposite side here, you get that saturation that we talked about. Once you're in debt sufficiently deeply, it doesn't matter anymore. It's all the same, no matter how much debt you have.
Is that actually based on something?
This is actually based on data, yes. So, student loans, I would argue, we're not so much in debt that you should not care anymore about more debt. Let's have a separate discussion after lecture. Make sure you don't lose all your money today. How does insurance come into play here? So let's say you have a lottery between $1,000 and $0, 50-50 chance. What's the expected monetary value? 500. On the average, you get 500. What is the certainty equivalent? Meaning, what that means is, what amount of money would you take instead of playing the lottery? So, would you say, if I gave you, let's say $900 guaranteed instead of having to play that lottery, would you take it? A lot of people might. Would you take $500 instead of playing the lottery? A lot of you might. Would you take $0? Obviously not. $2? Probably not. And so there's some sweet spot there where you transition from being willing to take the guaranteed money over the lottery. For a lot of people, that will lie around 400. People will be happy to take $400 instead of playing that lottery. If that's true, if that's what you're willing to take instead of playing the lottery, but if you were offered less, you wouldn't play the lottery. If you were offered less, you would take the lottery instead, then that's your certainty equivalent value. All right, this difference between 500 and 400, that's where insurance companies make their money, and why insurance is a win-win situation. Because if you were presented with this lottery, you would say, well, I'll take the guaranteed 400. The insurance company will come in and will say, I'll take that lottery from you. I'll give you the guaranteed 400, give me that lottery, and I'll put it into my big stack of lotteries. The insurance company has so many lotteries to play that for them, if you play 1 billion lotteries, you're going to get exactly the average pretty much. Law of large numbers tells you you'll hit it right on the average. So the insurance company is essentially guaranteed to hit that average. They're happy to play that lottery because they get to play it many, many times. You are happy because you got your guaranteed $400. And the difference here is $100. That's effectively where the market is for insurance. That's where they make their money. That's why this all works out. All right, so that's where insurance comes in. Now, this last little thing here, let's take a look at human rationality. So this is a psychology study. Let's do a little quiz here. You have two options. There are two lotteries you get to play. 80% chance 4K, 20% chance nothing, or guaranteed $3,000. Who picks A? So about 10 people pick A. Who picks B? Maybe about 10 times as much. So overwhelming preferences for B, but everybody can have their own utilities, function, their own preferences. Nothing's wrong picking the one over the other. Here's another choice you can make, C versus D. In C, 20% chance of 4K, otherwise nothing. In D, 25% chance of 3K, otherwise nothing. Who prefers C? Okay, good amount of people prefer C. Who prefers D? Almost nobody. So let's say overwhelming preference for B and C for those two cases. That's actually common. There's been studies, and that's what, on average, people would prefer B in the first case, C in the second case. Let's do some math. So people prefer B over A, C over D. If the utility of $0 is 0, which we know we can always do because we can shift utilities and rescale as needed to make this work, then B over A means that the utility of 3K is higher than 0.8 times the utility of 4K. If we also prefer C over D, what that means is that 0.2 utility of 4K is higher than 0.25 utility of 3K. If we multiply both sides with 4, we get 0.8 utility of 4K bigger than utility of 3K. Okay, that's what we have here. That's a contradiction, right? You have exactly opposite equality here between the two scenarios. What does that mean? That means is that the preferences that were expressed by a majority of the people somehow are not compatible with the actions we put forward at the beginning. Because those actions prescribe that you should be consistent. This is not allowed to happen, right? So how can we explain this? Well, there's a couple of things you can think of here. One thing is, humans just don't know how to make decisions. Just let computers and robots make decisions for us, and everything will be better. Another way to interpret this is that we didn't model these scenarios right. You could say, well, what's really going on here? In this scenario here, you don't just not get any money in this 20% of cases. You actually get the payoff of $0 plus feeling stupid. Because you could have guaranteed yourself 3K. Once you insert that, these equations change, because now it's not the utility of 0, but it's the utility of 0 plus stupid that comes into play. Whereas here it's just the utility of 0, right? So that's one way you can explain the preferences people have, and why even this is an apparent contradiction with the axioms, is just us not modeling the scenario exactly right. All right, next time we'll look at market decision processes.